Hey there. So now we'll be talking about the examples of polarization, but before that, let me give you a quick recap. So if we have a wave, for example, which is coming in towards a polarizer. So if this is the polarizer, for example, so if we have the wave coming in a direction like this, and then we have it exiting as well. So initially when the wave comes in, it has vibrations in all directions. Right? So the particles are vibrating at all directions, and all of these, by the way, are perpendicular to the direction of how the wave is going still. So after passing through the polarizer, what the polarizer does is that it only has the wave now. The vibration of the particles would now only be in one direction, perpendicular to the direction of transfer of energy. Here previously, again, this is like a 3D phenomena, so you have to imagine it as such. So all of these are in different directions, but these are still perpendicular to the wave. But after passing through the polarizer, what happens is now that these vibrations are only in one plane. Previously, these were in a lot of different planes, right? But now it's only one plane, which is also why this is also called plane polarization in your syllabus. So the idea about polarization is this, that we can say that when a wave is polarized, the vibrations of the particles are only in one plane, right? And needless to say, this is perpendicular to the direction of the wave, right? So to the direction of wave motion, or if I also say to the direction of energy transfer, it means the same thing. Now, one other important fact that you need to keep in mind when talking about polarization is this, that polarization only applies to transverse waves. It does not apply to longitudinal waves. And the reason for this is very simple to understand as well. Just let me write this down. So this is something which only applies to transverse waves. So if we had a longitudinal wave, in this case, the particles would be moving back and forth. So the polarizer, this plane polarizing filter, or the polarizer as it is called, cannot get rid of the vibrations, right? Needless to say, because of how parallel they could only be moving in the same direction. So they can only be moving in one direction. And the idea of polarization is that it could be perpendicular in many other directions, right? So we can plane polarize a transverse wave, but we cannot plane polarize a longitudinal wave. So it does not apply to longitudinal waves. So there's also this analogy that you can use to think about polarization and what it does to a certain wave. So if you had a rope, so you can create waves in any direction you like. You can make the rope go left and right like this, or in some sort of a diagonal direction as well, right, and up and down, and the wave would have the wave transmitted along the length in that direction, whichever you choose. But if you now have the same length of rope, but now passing through a small opening in a fence which is vertical like this, you know the only way the wave can get through is if you move the rope up and down. Now if you shake the rope in any other direction, a diagonal or a horizontal direction other than the vertical one, any direction other than the vertical direction, the waves would not be able to get through the small gap, right? So this is exactly what a polarizer or a polarizing filter does. So how do we actually calculate the impact the polarizer has on the light or whatever sort of a wave is incident on it. So let's say we have a polarizing filter like this, and also let's say that we have some sort of unpolarized light which is going to be incident on this polarizing filter. And something else which is really important about the polarizing filter is something called its transmission axis. So let's say the transmission axis of the polarizing filter is like this. What this really means is any sort of light which is going to be coming into this polarizing filter, now after passing through the filter, it will just be vertically polarized, right? So all the vibrations will only be up and down like this. So let's say this light which was incoming had vibrations in many different planes, right, just as we labeled before as well. So after passing through this polarizing filter, the only light intensity that we have is now in this direction as determined by the transmission axis. So as the transmission axis shows, this will now only be in the vertical direction. So now the vibrations will be like this, vertical, right? And now we talk about this in terms of the intensity, right? Basically, you can also think of it as the power of the power of the radiation or the light which is incident on this. So let's say if this is some intensity I which is being incident, right? So some intensity I of totally unpolarized light. When it passes through the polarizing filter, this intensity becomes half. And in a while, with the help of some mathematical equations, we'll see why this is the case, right? So I'm just writing this down here for you. Unpolarized light halves in intensity when it passes through a polarizer, right, or a polarizing filter. And by the way, this is not just restricted to if we have a vertical transmission axis here. Even if it was in any other direction, as long as you have unpolarized light coming in with some intensity, whenever you are restricting the basically you are restricting the vibration of particles to only one plane, the intensity becomes half. Usually this will not be tested in your syllabus. This is something which is just extra information for you. In your syllabus, you'll have questions like this, that you may have previously polarized light, which is then entering into another polarizer. So this is how the light was being transmitted previously. Let's take this part again. So let's take this part. And let's also have this part. Right, so this is the light intensity which is now incident. So as you can see, this is some vertically polarized light, right? So now the vibrations are only in the vertical direction, so it's either up or down. And now let's say there is a new polarizing filter here, and this polarizing filter has its transmission axis at some angle theta. All right. Now something very important to remember here is, right now I've labeled this theta with respect to the vertical, and this is not a convention. This is really just because this light which is coming in is vertically polarized. So something I'll write in a while as well. What you have to remember about this theta is that this is the angle between the incoming light intensity and the transmission axis. So it's the angle between them. So here, when this light is going to be coming in, this is the angle at which it's going to be incident on the filter. This is the transmission axis, and this is the angle, right? So if I have to draw this in terms of a wave, let's say this is the wave which was coming in, right? This was vertically polarized. Now afterwards when this polarizer is going to have some light exiting it, this light will now be polarized according to what this transmission axis determines, right? So what's going to be the case now is now this will be polarized at some other angle theta like this, right? This is what a polarizer does. Now after passing through the filter, after exiting this is now only along this axis, right? So it's polarized through this angle. So obviously there is going to be some change in the intensity, as we saw in the example above when we saw that analogy that we were drawing with the help of how rope waves are created in a fence, right? So there is going to be some relationship between them. So let's say this is some intensity I naught which is incident on the filter, and let's say there is some intensity I which is being exited from the filter. So these are related by this equation, which is also known as Malice's law, which is I naught cos square of theta, right? So this is known as Malice's law. So this is the equation which gives us the relationship between both these intensities. This is an important equation and you need to be aware of how to use this. By the way, this cos square theta does not mean it's the cos, it's not the square on the cos, because if you remember your math and your trigonometry, the cos can never be standing alone. It always has to be cos of something, because cos is just a ratio. So what cos square really means, cos square of theta, what this really means is cos theta, and that's going to be squared, right? This is just a way of writing this. So if you want to have a look at how exactly the intensity changes with different angles, let's make a table of this sort, keeping our equation in mind. So it's I equals I naught cos square theta. Let's make this slightly larger. So something like this. And then let's add some separators here. Right, so let's say we have we have some values of theta and we have some values of cos theta then, and then we also have some values of cos square theta, because the equation is I equals to I naught cos square theta. So let's take some extreme values, because we don't want to concern ourselves with values which are not as significant. So let's add theta as, so let's add it as 0, 90, 180, 270 and 360. So 0, 90, 180, 270 and let's make the last one 360. So like this, right? So theta is 0, 90, 180, 270 and 360. These are like the special values or related to sine and cos and tan. So if you find cos of 0, that's going to be 1. Cos of 90 is going to be 0. Cos 180 is going to be negative 1. Cos 270 is going to be 0 again. And cos 360 is going to be 1. Now if you take cos square, because that's what the equation says, and then I naught will be multiplied by the value of cos square. So square of 1 is 1, square of 0 is 0, square of negative 1 is 1, square of 0 is 0 again, and again it's 1, right? So now we know how this is going to be. So now let's try to plot a graph, and let's try to make this slightly smaller. Let's shift this here. And let's have the graph axis now. As you can see, in no part is the intensity becoming negative, right? Again, it's power. Intensity is basically power. So it's also pretty intuitive that it cannot be negative. So let's make the graph axis now. So it's like this. So on the x-axis we have the different angles theta, right? Right now we're looking at these in degrees, and right now on the y-axis we have the intensity values in terms of I naught. Let's mark the angles here. So this is 0, and let's try to make this a bit even, right? So this is 0, this is 90, this is 180. Actually, let's space these out even more. So this is 0, this is 90, this is 180, this is 270, and again you have 360, right? And let's see how the intensity values are changing right now. So I made a mistake here. Let's make it like this. Yeah. So at the angle of 0, cos square theta is 1. So I have the same intensity I naught. So I have the same diagram as above, only now I've made the filter a bit circular just to visualize this better. So right at the start, when the again we have vertically polarized light which is coming in. So right at the start, when the angle, when the transmission axis is at an angle of theta with the vertical, because again here we have vertical light incident, so we have the same intensity I naught that we get. So here, right at this instant. Then at 90, when this angle with the vertical is 90, the intensity drops to 0. So right at this point, the intensity drops to 0. Then when it's 180, it becomes again the same intensity once more. Then at 270, which is going to be now right here, so that this angle is 270, it's 0 again. And after one full rotation, so 0 is basically like 360 right now. So again we have the full intensity being exited out of the filter. So if we just join these with a smooth curve, again it's a prerequisite that you know the basic shape of a cos curve to make this entire sketch. So this is how it looks like, right? So from 0 to 90, the intensity falls. Then further from 90 to 180, the intensity rises again. 180 to 270, again it falls, and then from 270 to 360, it rises again. So this is the shape of the cos square curve. So the most important thing that you need to remember here is that this angle is the angle between the incident intensity. So incident intensity and the transmission axis, right? So the transmission axis, because in other questions you'll also have something like this where the light which is coming in may not be vertically polarized, maybe it's polarized in a different plane, and we'll do examples of this in the next video. So there you need to remember that it's not always the angle with the vertical. It is in this case because the incoming light was also vertically polarized. But in cases where it's not going to be vertically polarized, you need to think long and hard about how do you get that angle between the incident intensity and the transmission axis. So see you in the next one.